Imagine drifting silently through space when, suddenly, you look down and see your own feet stretching away from you. Ahead of you is a black hole, an object so powerful that even light cannot escape, and you are falling straight toward it. What happens next may be one of the strangest and most terrifying journeys the universe can offer. Black holes are often described as cosmic monsters, swallowing everything that gets too close. But they aren't giant vacuum cleaners roaming through space. A black hole is an incredibly dense concentration of matter, creating gravity so intense that the rules of everyday experience begin to break down. So, if you somehow fell into one, what would you actually see? What would happen to your body? And what would the universe look like as you disappeared beyond the point of no return? Let's take the journey. First, imagine approaching a black hole from a safe distance. At first, everything might seem strangely normal. You would still be falling, but if the black hole were large enough, you might not immediately notice anything unusual. You wouldn't suddenly feel an enormous gravitational pull from every direction. That's because gravity depends on distance. But as you get closer, something extraordinary happens. The side of your body closest to the black hole experiences a stronger gravitational pull than the side farther away. The difference may sound small, but near a black hole, that difference can become catastrophic. Imagine stretching a piece of dough between your hands. Pull harder on one end, and the dough elongates. Now imagine the universe doing the same thing to you. This is called spaghettification. The name sounds almost funny. The reality is anything but. Gravity would stretch you lengthwise toward the black hole while simultaneously squeezing you from the sides. Your body would become longer and thinner, like a strand of spaghetti. Why does this happen? Because gravity gets dramatically stronger as you get closer to the black hole. Your feet, for example, might be significantly closer to the black hole than your head. That means your feet are being pulled more strongly than your head. The difference between those gravitational forces is called a tidal force. And near a black hole, tidal forces can become enormous. For a relatively small black hole, spaghettification could happen before you even reach the black hole's boundary. But here's where things become even stranger. Every black hole has a region called the event horizon. Think of the event horizon as an invisible boundary around the black hole. It isn't a solid surface. You wouldn't crash into it like hitting a wall. Instead, it marks the point beyond which escape becomes impossible. Once you cross it, there is no turning around. Not because your engines aren't powerful enough. Not because you're moving too slowly. But because, according to our current understanding of physics, every possible path forward leads deeper into the black hole. Even light cannot escape. And that creates one of the greatest mysteries in the universe. What would you see as you cross the event horizon? If you were falling into a supermassive black hole, the experience could be surprisingly uneventful at the horizon itself. Because the black hole is so enormous, the tidal forces at the boundary could be relatively weak. You might cross the event horizon without feeling a sudden jolt. No alarm, no flashing sign, no cosmic wall, just empty space. But something else would be happening. The outside universe would begin to look increasingly distorted. Light itself would be affected by the black hole's gravity. Stars could appear shifted, stretched, or warped around the darkness. The black hole would bend the paths of light traveling nearby, creating bizarre visual effects. And time would begin behaving in a way that seems almost impossible. This is where the story becomes truly strange. From your perspective, you would continue falling. Your own clock would appear to tick normally. You wouldn't feel your personal time slowing down. But an observer watching you from far away would see something very different. As you approached the event horizon, your signals would take longer and longer to reach them. Your movements would appear to slow. The light coming from you would become increasingly stretched toward longer wavelengths, growing dimmer and redder. Eventually, you would appear to fade away. To that distant observer, it could look as though you never quite crossed the event horizon. But from your perspective, you would cross it. And once you did, there would be no message you could send back saying, "I've made it." Because the event horizon is a one-way boundary. And then comes the final destination, the black hole's interior. At the center of a traditional black hole, our current theories predict something called a singularity, a region where matter is compressed to an extreme and where our existing understanding of physics breaks down. But here's the important part. We don't actually know what happens there. General relativity predicts one thing. Quantum mechanics tells us that our description cannot be complete. Somewhere inside that darkness is a mystery that modern physics has not yet solved. And this is why black holes are so fascinating. They aren't simply places where things disappear. They are laboratories for testing the deepest ideas we have about gravity, space, and time. They force us to confront a strange possibility. Perhaps space and time themselves are not as absolute as they seem. Imagine watching a clock near a black hole while another clock sits far away in deep space. The clocks wouldn't necessarily agree. The closer you get to an intense gravitational field, the more slowly time passes relative to someone farther away. This effect is called gravitational time dilation. And it means that two people can experience time differently depending on where they are in the universe. One person could spend a short amount of time near a black hole while much more time passes for someone far away. So black holes don't just bend space. They bend our intuition about time itself. And that leaves us with one final, haunting thought. If gravity can change how quickly time passes, and a black hole can trap you beyond a boundary where the outside universe can never receive your messages again, then when you fall into a black hole, whose version of time is the real one? Yours or the universe's?